Good afternoon. Some of you, I just left the room after office hours, and some of you I did not see today. I'm recording this video, keeping in mind people both who were in class today and people who weren't. What you're looking at on this screen is what students walked into the classroom today and saw. And all I had asked them to do was choose a random space on this page and make rectangles so that they contained 50 letters inside them. And I asked them to do this 3 times just to show you what this looks like. The first side of the page had this description that said something like this. Just try to find a random spot. You can make a 5 by 10 or a 10 by 5 or a 2 by 25, whatever you want to do to select 50 letters. And of those 50 letters, count how many O's are in them. So in this example, in blue here, there are 50 letters selected, 28 of them are O's. This is another selection, 25 are O's, and here's a third selection of 50, 24 are O's. Those are 3 different sample proportions. If I were to just say, what's the proportion of O's in each of those? This might say sample proportion 1, 28 out of 50 is 0.56 or 56%. Sample proportion 2 is 25 out of 50 or 50%. And sample proportion 3 is 24 out of 50 or 48%. I didn't tell students until after they had done this, but what this table is it perfectly matches the results of the 2012 presidential election in which Barack Obama received 50.6% of the popular vote. So in this table, of course, you can't see 50.6% of the letters in this table are O's to represent a vote for Barack Obama. R's represent a vote for Mitt Romney, and T's, there not very many of them. That would be a vote for a third party, someone who wrote in someone other than Barack Obama or Mitt Romney. So the idea here is by selecting 3 is you've created 3 sample proportions, akin to going out and interviewing people or calling people randomly and saying, who do you plan to vote for in the presidential election? And say you talked to 50 people and 25 of them said they were going to vote for Barack Obama, or 28 said they were going to vote for Barack Obama, or 24. The idea here is that wouldn't be a sign that something was terribly wrong. If you talk to a different group of 50 people, you would get a different number, likely get a different number of Barack Obama supporters back in 2012, before the presidential election. The reason that I start topic 5 with this is to give you a real solid, concrete example of sampling variation, because it gets very abstract from here. The reality is we don't take many samples. We take 1 sample and we have to understand how it's going to be, how it behaves. And everything I'm going to talk about moving forward is a theoretical infinite amount of samples would distribute a certain way, and we could make predictions and we would know how bizarre. So notice that 28, 25, and 24 are all different numbers, but they're not terribly different numbers. So the idea here is this is natural sampling variation. There's no bias in the way that I selected these rectangles. I just selected a point and made a rectangle, not really caring what letters were in them, and it just happened to get 28, 25, 24 O's. That is natural sampling variation. 1 sample will be different from another, but only so different. There's only so much variation that makes sense. So I'm going to switch my screen here and show you the result of what happened in class today. So in class, my first 3 examples are there, and each student in class collected 3 samples. And the column B here is the number of O's in their rectangle, and column C is the sample proportion. I'll talk about column D in a second. But notice that on all these, you see differences in numbers. I see some 60%, I see some 40%, I even see some 30%, but I don't ever see 20%, I don't ever see 70%. So this really shows that all the samples that came out of the whole room full of people varied, but they only varied so much. So with that samples, the smallest value in the room was 36%. The largest value in the room was 66%. This next column D is to combine and say, well, why would you call these 3 different samples? Why don't we just say, I talked to 150 people. This 50, and this 50 is a total of 150 people. So this number is all these O's together, my 28, 25, and 24 O's divided by 150. It's also the average of my 3 sample proportions. So my average came out to be about 51.33%. And you can see that people had different average percents down the line, but now we're starting to even look more similar, 52%, 57%. I don't see any 30%. I don't see any 60%, anything in the 30s or 60s. So this next part is said when we looked at those 3 samples combined, we had a larger sample, and look what happened. The numbers got closer together. There was less variation with larger samples. This is basically going to move on to the idea that the larger your sample, the more reliable it will be. And if you took a sample of 1,000 people and then a different sample of 1,000 people, the results may be different, but they should be a lot closer than in small samples, like samples of 50. And you'll see here that the minimum value here was 42% and the maximum value was 57%. So of these, what you see here is the average of this came out to be 0.502. Notice that that average is very close to what happened in the 2012 election, where Barack Obama received 50.6% of the vote, 0.506. In the standard deviation, which is calculated by finding that average and subtracting that average from each of these individual items, and then squaring them and adding them all up, and sort of an involved calculation with all this data, it worked out to be about 0.07486. And I'm gonna point out how similar these two numbers are, but I'm not gonna, we'll talk about that in a second. First, I just wanna pop over to a different document. And for those of you coming to class on Wednesday, this document I'm going to print and hand out to each of you. So you'll get a copy of this. So don't feel like you have to take all these notes or copy it down verbatim, because I'm going to give you a printout on Wednesday. So this sort of just describes what happened today. You were given this table in which 50.6% of the letters in the table were O's to represent the 50.6% of the popular vote that Barack Obama got in 2012. So in this case, the population proportion is 0.506. And elections are a rare case where we actually get to know the population proportion, because we tally all the votes and put all the effort that goes into election day in order to see that. In this case, each class member found 3 distinct sample proportions, each of size 50. As soon as we know this information, that P equals 0.506 and N equals 50, we can make a theoretical sampling distribution. So notice that if it's true that 50.6% of the population is going to go out and vote for Barack Obama, and we were going to talk to a sample size of 50, we can make predictions about what we'd expect. So based on just those 2 numbers, the result of the election and the size of our sample, we could see that using a calculation, we can come up with a prediction for standard deviation, which would basically say that 3 standard errors below the population proportion and 3 standard errors above the population proportion is pretty much all we should ever see. You should not see samples go lower than this number or higher than this number. So this sampling distribution would be centered at the population proportion. 0.506 is in the middle. Samples should be pretty close to 0.506, but not exactly 0.506. In fact, technically, if we talk to 50 people, if you divide any whole number by 50, you're just going to get an even percent. So notice that all our results would be like 48% or 50% or 52% or 54%. You actually couldn't get 0.506. So samples would be close, but not exactly. So how much variation is reasonable? We didn't see too much variation. Remember, the class never saw any results in the 20%, and they never saw any results in the 70%. Well, that prediction for standard error is done using this calculation, which would really, this says the standard deviation of sample proportions, that p hat would represent sample proportions, can be done with this equation. This is often called standard error, which is really a mathematical prediction for standard deviation, because standard deviation is calculated using data, and you don't actually use data to come up with this. You just use sample size and the population proportion. So this is how that calculation would work out for this scenario where n is 50 and p equals 0.506. If you weren't in class today, I encourage you to make sure you can do this on your calculator, because this can be a calculator error if these numbers aren't entered right. Make sure you can enter this and pause the video if you need to, and make sure you get, I think it's 0.0707, but it would round to 0.071. So the distribution above is just centered at 0.506 and then adding 0.071 plus 0.071 plus 0.071 minus 0.071 minus 0.071 minus 0.071. A couple things on the symbols that are come up. The symbol mean sub p hat you could read that as the mean of all sample proportions, as in, so in our case, when we did this, our sample proportions averaged out to be 0.502, but this isn't just our class. It would be if infinite sample proportions were collected, those should average out to be exactly what the population proportion. So if I kept doing this for years and years and years with all my classes, this should come to an average of 0.502. And this is where I'll point out now, note that this is the actual standard deviation of these decimals here. And our prediction for standard error is really close to that, 0.707 versus 0.071 versus 0.075. Those are very similar numbers. And with the sample size of 150, that would change the standard error because you're dividing by 150 instead of dividing by 50. And look at the prediction would be 0.041. And in the classroom, it turned out to be 0.048. This would be considered more accurate because we only had about 48 different samples, whereas this is if you were to collect infinite samples. Okay, also done with the same calculation. Going back to that document. The symbol, this is what we just talked about. This is standard deviation of all sample proportions, assuming infinite samples and all possible sample proportions. Just going to look this over and make sure if there's anything else I wanted to see. So in our class, if you made a dot plot of all the samples, it worked out like that. I just want to point out kind of compared to the image I just showed you, where really 0.293 is at the low end and 0.719 is at the high end, that all these fit within that distribution. And you can almost start to see a normal shape here when you do that. Below, I combine these with all the data I've done with all the classes that have done this before and gone through the same activity, and notice that it really starts to be similar. This dot plot is every student in my Math 146 classes that went through this process and their result, and it really does fit in that normal distribution. So even if you think, well, those two things don't look very similar, but agree that this is starting to look more similar, this does take going on the faith that moving forward, if you were to do this infinite times, not 48 times, not 300 times, but infinite times, that these dots would eventually stack up to be a perfect normal distribution. And this is going to be a key idea as we move forward, that we can, so remember, in reality, we're just going to end up using one sample. And the stuff we move to next is that when you get just one of these dots, let's say it's this dot that I'm hovering over right here, just say, well, is that the right answer? It's like, well, it could be, but the reality is it's probably a little bit off. Things like margin of error are going to be related to this, and how this is calculated are all based on this normal distribution. There's one little more thing about the sample size has to be large enough, but I think that's probably enough information for now. We'll save that for Wednesday, and you'll also come across it in your readings. So if there are any questions coming up on this video, I'm going to post it on WAMAP, so you can post them there. And I also encourage you to return to this video once you've played a little bit more with this, once you've done the topic 5 reading, maybe even once you've started writing confidence intervals, to just remind you where all this stuff comes from. Again, my goal here is to give you something concrete like having the actual physical experience of creating a sample about a very abstract idea that in the end, you're going to be able to tie these things together. Thanks for watching.